Where's Scott? We were supposed to do this video like 20 minutes ago. Wait a minute. I think I hear him.
He spent a long time cleaning around that closet. I haven't seen him since. And there it was! Old Man Winkleton! Oh. Sorry, Professor Barrington. We have to do this another night. Scott's a nerd here. Let's get started. Let's go this way. Mr. Barrington will be okay. So, what we're talking about tonight is a question that was on the original homework I gave you. Now, first thing we're going to do is we're going to start, you know what? I hate this board. Let's not write on this board anymore. Let's write on our brand new board! Look at this. I mean, it's brand new to me. It's brand new to Colby. It looks like it came out of an old World War II elementary school, but it's okay. It's ours, it's large, and it's my perfect height. Okay, so like I was saying, we're going to be going over problem 13 from chapter 2. I'm going to bring my book over here, and I'll set it over here. Whew, I thought it was warm. Okay, anyway, problem 13 goes as follows. Where is it? Okay, a person takes a trip driving with a constant speed of 89.5 kilometers per hour. So, look at the space, it's amazing. So, 89.5 kilometers per hour was their constant speed. So we already got a speed. We're done. No, just kidding. I say kilometers per hour, right? Kilometers per hour. Second. Okay, except for a 22-minute rest period. Okay, once again, I see a problem right off the bat. 22 minutes, well, it's in minutes. We don't want minutes. So before I even continue the question, the reason I don't want minutes is I can see I have hours right here. Technically, I could always turn this into hours and keep this as, turn this into minutes and keep this as minutes. But this is bad math, bad science. We almost do everything in hours or seconds most of the time. Okay, so let's do 22 divided by 60. That will give us 0.366666666666666666667. What was I talking about? Hours. Okay. So 0.37 hours about. And yeah, I just did that so we can simplify things a bit. Okay, let's continue. What else do we need now? If the person's average speed is 77.8 kilometers per hour, so if their speed average is 77.8, I believe, 0.8 km per kilometers per hour. What else? How much time is spent on the trip, and how far does the person travel? Okay, the time one is the hardest part of this problem by a lot. And it's not because of what we know. It's because of the algebra. The algebra on this one is actually a little bit more strenuous. Okay, let me show you why. Let's take our base definition. Okay, average velocity. It says average speed. Well, it's the same thing. We'll say average velocity average. We know is defined as our total distance divided by our total time, right? And we know that those two divided by each other will give us our 77.8 here. Okay, now we're like, but Mr. McLeod, but Scott's a nerd. What we're trying to find here is time. We're not trying to find average velocity. Well, we're going to use average velocity because that's the information we got. And we're going to use our velocity to figure out both of these. And if we can figure out both of these, we can figure out this one. Okay, that's where it gets a little tricky. And we'll change colors here. So we know that we're staying separate from all this stuff. We're going to start our equation. Okay, so first, total distance. Well, do we have any distances on the board? Do this. Yeah, we don't. So, because we don't have any distances on the board, we have to make them, right? So we have a velocity and we have a time. Well, this velocity does not go at this time. Remember, this was our time resting, so put an R there. We don't know our time traveling. I'll do TT, time travel. Not time travel in the future. Nothing, no Marty McFly going on here. Just time traveled on this trip. Okay, so let's do that. We know that velocity, this velocity, I'll do T for the trip, times time of the trip will give us distance. Remember our base equation? What is our base equation? It is velocity equals distance over time. And we're solving for distance, so velocity times time equals distance, right? We just rearranged it. Cool. Just making sure you know where that came from. Cool. So that's why we got this. Okay, so we got that. Velocity times time. Plus our second velocity times time. Well, how fast were we going? According to the book, we weren't moving at all. It said this is how long we were resting. So it's just 0 times that other t, right? Cool, we got that. And so that becomes 0. But we'll deal with that in a second. Now, let's do the bottom part. So far we have one unknown value, because we know what the velocity is. We just don't know what time is. Okay, now let's total just our times. Okay, 22 minutes, so 0.37. We have to once again use our other time that we don't know yet on the bottom, because we got to get our total distances and total times. Remember, we just used our unknown time here to figure out our distance. This doesn't count as one of our times. So we're going to use that same variable down here, t of t. Okay, and what does that equal? Well, we're using this equation is the same as this equation, total distance, total time. So it's 77.8. All right, now you're like, oh, by the way, we got to add these together. To make it easier to see, I'm going to take all my plus signs and do them in a different color, just so we know they're not t's, they're pluses. Okay, cool. Okay, first thing I do, I look at this and I say, well, 0 times t, I know that that one just goes away. There's no distance there, because we were resting, right? Logically, we just know. So that one goes away. All right. Velocity, well, what was our velocity? 89.5. So we'll plug in 89.5 right there. 89.5 right there. Cool. And now we somehow, well, if we look at this, we have 1, 2, 3 known numbers. How many unknown numbers do we have? Well, if you say 2, you're wrong. We have 1 unknown number. This is the same thing as what we don't know here. Somehow we got to get these together. And you can't don't make the mistake of just trying to divide these. This addition makes it so you can't do that. So what we got to do instead is we got to multiply both sides by everything that's down here to get this over here. So we know that if we do t of t plus 37 up here, and we'll do t of t plus 0.37 here, okay, I'll do that in parentheses, because remember this is being multiplied. We know that this upper one, paper towel. There we go. We know that this upper one canceled out this bottom one. Okay, we're a little closer, but still, I still can't just divide out the t. I mean, I could, but I'd be back where I started, right? If I just divided by t, I'd end up with t on the bottom, and then I want to throw it back over there. We'd just be in circles all day long, and I gotta get back to story time, so that's not happening. So what we're going to do instead is we're going to move all of this over there. You're like, but Mr. McLeod, that'll leave 0. Well, good. We want to leave 0 over there. So over here, we're going to do a minus all of that, then in parentheses, 89.5 t of t. Awesome. So that got rid of this. Now we can start doing the magic here, right? I can now pull t out of these problems. And by the way, we don't need this parenthesis on this one, do we? Okay? So, before I do that, let's divide, let's do our 77.8 times both of those. So we get 77.8 t, remember, that's trip, time of the trip, plus 0.37, well, it's 0.37 times 77.8, right? Because we got to make sure we're factoring into everything here. So let's do that. We'll just do right here on the calculator. So I'm taking 77.8 and multiplying by 0.37. And we get 28.786. So this is 77.8t plus that new number, 28.786. Okay, now we have a number, and that's minus 89.5 t of t equals 0. Well, look at this. I should have done these in different colors to help everyone see a little better, but we now have a variable on two of them, and we have just a flat number by itself. Let's get that number out of there. If we get that number out of there, we can then extract t from both of those. So let's do that. Let's move that over here. What does that become? Well, that becomes negative 28.786. Remember, I just subtracted it from both sides. That's all I did there, which means it goes away here. And what are we left with? Well, we're left with 77.8t and 89.5t. Look at that. We have one variable in both situations. Well, those of us that know our basic algebra, we know that we can, let me draw these a little closer to make it look a little bit more normal to you, 77.8 t of t. We have the variable here, the variable here. So the way we do it is we're just going to pull it to the front of all of that. And you guys see how I did that? I just basically reversed it. Because technically I could do this times this to get this back, and this times this to get that back. This is the same thing as what we were doing before. I just broke it apart a little bit, right? This is important. Now we just have two numbers. Well, let's simplify those two numbers. 77.8 minus 89.5 gives us negative 11.7. So this simplifies. Okay, at this point I'm just doing algebra steps. Not a lot of physics here, right? Negative 11.7. Okay. And at this point you should be able to do this pretty easily, right? We have a number, we have a variable, we have a number. We're going to divide this number by that number to get that number. Okay, so 28. And I'm just going to do positive because they're both negative. Two negatives make a positive, right? 28.786 divided by 11.7 gives me a time of the trip of 2.46. Okay, so that's our total time of the trip so far. All right, now that doesn't include the time rested, right? This was just to figure that out. Well, what are we looking for again? Let's not lose track of what we're doing here. How much time is spent on the trip? Well, it's this number plus that number, right? It's our trip time, our traveling time. That's what that stands for. Remember, T stands for traveling. And our resting time, T of R. Well, let's add those together. 2.46 plus 0.37. And we get 2.83 seconds. Okay, well, let's make sure that's right. Let's check the answer in the book. Okay, I think that sounds right, but who knows? I don't know how many times I've made a mistake and then regretted it later on. I'm talking about physics here, not anything else. Chapter 2, number 13, 2.8. And by the way, that's hours, right? That makes sense. 2.8 hours. Bingo. Right on. Physics works. Now, the second part of the problem says, find the distance, the total distance. Well, that's easy now, isn't it? Do we have any distance when we are resting? No. So we don't even worry about that. So part B, find the total distance, that doesn't matter. None of this matters anymore at that point, right? Because we traveled. We know that our speed, our velocity, during the time we were moving was 89.5. It said it was constant. First thing it said, right? Even though with the rest, it kind of evened out to this. Just when we were moving, we went this speed, and we did it for that long. So, what is distance? Remember, it was speed times time. Velocity times time gave us distance. So, we're just going to take that time. I already have it on the calculator from before. And I'm going to multiply that by 89.5. And I get a big number. I get 253.3 kilometers. And one more time. I should have left the page open. Let's check the book. What does it say in the book? Wow. I thought I flipped right to it. I didn't. Let's say in the book, 13. 218. Okay, so I'm a little bit off. Why am I a little bit off? 89.5, 2.83. Well, let's try to do it with a 77.8. Maybe, oh, you know what? I bet they want to know the average distance. Yeah, I need to read it a little closer. So let's try that. Let's try with that. 77.8 times 2.83 gives me 220. That's a bit closer. 218. So that's what they're actually going for. Average velocity and time. Okay. I think it says the average distance and not the total distance. Because the total distance should just be I got it there, right? All right. Well, that's physics and math. And Scott's a nerd. I'll talk to you guys later.